Assalamualaikum and good afternoon.
وعليكم السلام ورحمة الله وبركاته.
So we continue our lesson on the six lessons: linear displacement and position transducer. So we will try to finish this part of the lesson. So basically, in this part of the lesson, we will look into the application of LVDT, potentiometer, capacitive transducer, and strain gauge in displacements transducers. So we start our discussion or lecture on LVDT, or so-called as linear variable differential transformer. So this device is inductive type and a passive transducer, whereas it require a power supply to operate. So the construction of the basic LVDT is as can be seen from this figure. The LVDT basically have two parts of secondary windings, okay, and located on either side of the primary winding. So it has a primary winding where an AC supply is given to the primary winding. So when current flows through the primary winding, electromagnetic flux is generated. So basically, the winding is it is in the place around a hollow cylinder, and inside the cylinder there is a core, highly ferrimagnetic material. So this core basically move to the to the left or to the right to represent the displacement. So basically the core is linked to the object that we want to measure the displacement. And on the side of the primary, on each side, there is a two set of secondary windings. And the secondary windings connection is shown as in figure C on the left here. So that the output, the total output, okay, will be the difference of EMF generated, the EMF generated between the first part of the secondary and second part of the secondary windings. Okay, so basically when the magnetic field is generated by the primary, the magnetic flux will be coupled, okay, to the both part of the secondary windings, and the amount of magnetic flux that couple to the secondary windings, okay, will determine the output value. So, for instance, here, okay, in the example, if when the core is at the center, the amount of electromagnetic flux that link to the first part of the secondary and the second part of the secondary are equal. So therefore, the electromagnetic flux or electromagnetic force or voltage that induced on the secondary, first part of the secondary and second part of the secondary are equal. Therefore, the output is equivalent to 0. So the output, so we have a first E1 here is measured. This part E2. So basically, the output, okay, let's say we say the output E out is equivalent to E1 minus E2. Okay. So when the core is at the center, so it means that the amount of flux electromagnetic flux that link or couple to the both part or first part of the secondary and second part of secondary are equal. Therefore, the output is equivalent to 0. So the output is made here is represent the amplitude, representing the amplitude of the AC output. Okay. So when the core move, let's say, to the left, okay, to the left hand side, so there will be more electromagnetic flux link to the first part as compared to the second part. So when it moves towards to the left, so E out, the output or the amplitude across the second part is larger than the amplitude output, the amplitude of the output at the second part of the secondary. So and basically, so the output will be positive or when it move to the left, okay, because the E out is measured at E1 minus E2, okay. But at some point of the displacement, so this is the displacement to the left, the our output E out, okay, will start to diminish or disappear, because when it move to the left, further to the left, the core is moving out from the center of the LVDT. So there will be no significant electromagnetic flux couple, okay, to either first part of the secondary or to the second part of the secondary. So here we will see the E out will start to drop. Okay. So in this figure B, basically representing the absolute value, but the actual amplitude, okay, is represented by the figure D. So when the displacement go to the right, okay, so the amplitude output at the second part of the secondary is much larger than the output amplitude at the first secondary. So so as the core move to the right, or the displacement move to the right, so the output is decreasing, okay, linearly. But similar case when it has exceed, okay, the boundary or the limit of the position or the core, okay, and when it the core lift out from the center, so the output will start to diminish or gone. Okay, so this is what I have explained basically. So again, okay, when the core move to the left, the first secondary is much stronger, so the link magnetic field is much larger than the secondary part. Okay, so because the output voltage in which the phase is in phase with the primary voltage basically. Okay, but when it move to the left, okay, move to the left, sorry, move to the right, basically the output or output is 180 degree out of phase. Okay, so that is represented by the negative value of the amplitude. So so it can be used to determine the you can be used to determine whether the displacement direction, whether to the left or to the right. So the advantage of LVDT, it has a high degree of robustness, whereas the movement of the core is smooth with small friction. So the surface is basically very polish, so that it move uh, uh, move nicely or smoothly with very minimum friction. And is suitable for detecting a very small fraction of movement, and the output can be amplified or with signal conditioning gain. Okay. The disadvantages of LVDT, it is easily influenced by magnetic field, because this is a inductive device, so it must be used or away from noise that is produced by other magnetic field source devices. So and then another advantage that that not listed here is that the output or the sensitivity is linear, whereas the relationship between the output and the displacement uh, within the limit of measurement is highly linear. Some application of LVDT is used in automotive, like for example in racing vehicles, and then the free core of linear variable differential transformer used in R&D for to check the uh, performance and profiling of the damping system. And also the profile is used, okay, to analysis the car for performance when it's drive on a certain circuit, and the car can be tuned according to the conditions. Okay, so that is basically the application of LDT, where it does not add any extra force when it's applied to like in this system applied to the damping system. So because of the movement of the core is smooth, there's no friction, right? So let's see in at this problem, LVDT. Um, so this in this problem, an LVDT is connected to an amplifier with a gain of 250. The output terminal of which are connected to a 5-volt voltmeter. Okay. So the voltmeter scale can be read to 1/5 of a division and has 100 division in all. So given that a core displacement of 0.5 mm provide an output of 2 millivolt from the LVDT. Okay, so that's one of the outputs given okay, from the LVDT. Okay, wow. So find the sensitivity of the LVDT. Number 2, the sensitivity of the whole system. Number 3, the resolution of the instrument in the centimeter. I mean the resolution of the basically the whole measurement or the whole measurement system. So in this problem we have a LVDT. So LVDT, let represent it. Okay. So it basically measure the displacement. So and then they have a E out. Like to gain a factor of I put um, a symbol here. Gain amplifier with 250. And connected to a voltmeter. So this is a 5 volt full voltmeter. Okay, so this measure from 0 to 5 volt. Okay, it has 100 division. The division 100, and each division uh, can read to 1/5. Okay, so first we find the sensitivity of the LVDT. So sensitivity number 1 is equivalent to the change of output over change of input. So here it only give one point. Okay, let's say the output E out and the displacement. So it only one set of output, which is 0.5. The output is the amplitude of the output is 2 millivolt. Okay. So LVDT, when it's at the center, the coil is at the center, means that the displacement is 0. The LVDT output is equivalent to 0. And we know that the characteristic, okay, of LVDT, the characteristic there for LVDT, it has a linear, okay, response. So we can measure the output at 12 millivolt, and we find the sensitive. We find the from the slope, okay, 2 milli minus 0. Yeah, so one output point, and then the origin 0.5 minus 0 volt per mm. So we get that the sensitivity is 4 millivolt per mm. So that's the sensitivity of the LVDT. So this part. Okay. Okay, so the sensitivity of the whole part. So we have to consider the amplifier gain to find the sensitivity of the whole part. So is equal to the amplification factor times the sensitivity of the LVDT. Therefore, 250 multiply with 4 millivolt per mm or millimeter. So we get 1000 millivolt per millimeter. So that's the whole sensitivity of the sensitivity of the whole system. So next we need to find the resolution of the instrument in centimeter. So the resolution of the instrument in centimeter. So the voltmeter can read up to 5 volts. That's the maximum. So the voltmeter 5 volt. So basically, by definition, resolution is okay, so the sensitivity, the resolution of the instrument, okay, can be uh, retrieved or calculated by uh, knowing the minimum voltage that can be read by the voltmeter divided by the sensitivity of the whole setup. Okay, so now we need to know the minimum voltage that can be read by the voltmeter. So minimum, we need to know minimum voltage that can be read by the voltmeter. We need to find. So there are 100 division. 100 division. So there are division. There are 100. Okay. So it used to measure from 0 to can measure from 0 to 5 volt. Okay. So one division can basically read 5 divided by 100, which is around 50 millivolt. So for each division, okay. So there are 100 division, so on. Okay, but each division, okay, can read 1/5. Okay, so so you have one division. So there are smallest. That's all called as a scale. Okay, so each scale can measure 1/5 of the division. Okay, so scale can read 1/5 of a division. Therefore, the minimum voltage that can be read is equivalent to 0.05 or 50 millivolt divide 5. So we get 10 millivolt. Okay, so each scale can measure 10 millivolt. So the resolution. So here in a minimum, so we get 10 millivolt, and the sensitivity for the whole system 1000 millivolt per mm. Sorry, 1000 millivolt per mm. Okay, so we get the resolution is 0.01 mm, but the resolution in centimeter is 0.001 centimeter. That's the resolution. So that's the small resolution of the smallest resolution, okay, of the displacement the system, okay, can detect and show on the voltmeter, 0.001 centimeter. Okay, so there's another uh, variation of LVDT. It's called as differential variable reluctance transducer. So it is for critical linear displacement measurement, and the resolution is up to micrometer and can go down to sub-micrometer. So the core position is detected by measuring the coil differential magnetic reluctance using a sine wave excitation and synchronous demodulator. The operating of this LVDT, the VRT is around up to 175 degrees Celsius, and the frequency response is up to 20 kilohertz. It's made of stainless steel and high performance polymer, waterproof and frictionless. So the application here, uh, it is used for automotive and also robotic system. And there are other application is listed here, but one of the significant application I want to share is the for biomedical sensor for measuring strain in bone and soft tissue, where surgeons or doctor during the operation they can use DVRT. They use DVRT to poke on surface of tissue, so they can know the uh, stiffness of the tissue. So so healthy tissue has different response uh, to unhealthy tissue. So let's say in application of removing tumor, so the surgeon can identify the surface that need to be removed. Okay, so that there will be no uh, unhealthy tissue left during the operation. So the operation is, I mean, the principle is similar, but okay, the DVRT or differential variable reluctance transducer, the similar in terms of the similarity with LVDT combined with their signal condition to convert a linear displacement into a linear variable electrical output signal. Okay. So the displacement LVDT DVRT is detected by the movement of a coil within the coil inside the sensor. Okay. And the difference between the sensors is in the coil format. As you can see on the right here, for DVRT, uh, it uses center tap uh, transformer. So That's the only difference between the LVDT and DVRT. Right. Now we have other type of linear displacement transducer, which is a potentiometer. So a potentiometer basically a resistive transducer contain a translational or angular displacement shaft. So this shaft drive a wiper in the transduction element that slide along the resistive layer. Okay, so there are basically 3 points on the resistive transducer, as we can see in the figure, point A, C, and B. So C, okay, is the moving part of the resistive transducer, so called as the wiper. So this wiper, when it move, basically due to the displacement, it will change the total resistance between A and C and between A, C, and between C and B. So, and also it can be made into angular displacement sensing shaft. There are few types of potentiometer, linear potentiometer. So the resistance between the wiper and one end terminal is proportional. Okay, and then the logarithmic potentiometer, where the distance between the wiper and one end is proportional to logarithmic function of the resistance between them. And potentiometer with switch, same as linear potentiometer, except it has a switch mounted on its back, or that it has a dead section in one of the resistive element. And high power type called as rheostat, as we can see in the figure. So the material, the main material that made of the potentiometer, there can be carbon deposited. So this is the common material, high, low cost, has a reasonable lifetime, and the noise level is acceptable. Then we have a ceramic material or ceramic metallic, high quality trim pots, low noise and high stability. Also, it made of conductive plastic, high quality and excellent life cycle, and low noise and very good mechanical experience. We has where the transition or the movement of the shaft is smooth. And then wire wound, high power, almost indefinite life. Okay, and then the resistance is granular with discrete small step rather than it completely smooth transition from one resistant winding to the next. Means that at a bit cost, and it is low noise, usually a rough mechanical feel. Okay, not so smooth or the movement. These are the type of potentiometer. It can be seen. Okay, they are regular size. Okay, this one is the angular potentiometer displacement potentiometer. Okay, and there are small package potentiometer, and then there are even smaller package. This is a linear potentiometer, sliding potentiometer. So it is regularly used to adjust this sound, okay, sound quality parameters such as loudness, pitch, frequency, and so on. Application. And this is the one of the applications of potentiometer, where it is used to measure the level of fuel inside a vehicle tank. So basically, the potentiometer moving shaft or moving part is linked, okay, to a float. So the link is done very carefully so that there is no so that the inside part of the tank is separated from the outside. As the float move, so it will move the shaft or slider and then change the potentiometer resistance. So the typical way how to convert, okay, the output of the potentiometer to voltmeter is by using a power source or power supply. Okay, so basically the output, okay, is proportional to the displacement or to the position of the float. This is another example of sensor position using angular movement potentiometer. So in this application is to use to detect the angular movement or the angular displacement of a motor, and the gear ratio is used so that the ratio of the movement of the potentiometer is reduced. Okay, and basically the output, okay, is converted to a ADC, analog to digital converter, where the output is basically basically the output is basically changed into binary values. Okay, so it here due to the gear ratio, okay, to ratio 1, so the when, okay, the angle arm angle move, like in this case 10 degree, the potentiometer is changed by 20 degree. Okay, so and then the potentiometer output, okay, here, okay, given in this example is 0.29, and the ADC output is 0.0001, 0.1111. Okay, so the calculation of the ADC output is based on the formula which we have covered in the previous class. So here, 2 to the power of n multiply the analog input divide by the reference voltage. Okay, its reference voltage is 5 volt. Okay, and the analog input in this in 10 degree change of the arm angle is 0.29. Okay, divide by the basically 2n is the bit number of the ADC. Okay, number of bit in ADC. So here the output is 2 to the power of 8 multiply, okay, with 0.29 divided by 5, and then into binary value. Okay, so here is one example how the potentiometer is used for to detect, okay, the angular movement, okay, of a robotic arm. So you see the range, okay, of detection is between 0 to 5 volt. Okay, so the maximum is at 350 degree. Okay, so because this is the okay, potentiometer, so basically the angle maximum that it can detect is around 175 degree. Okay, let's look at this problem, or okay, we do an exercise. Okay, I give you about 3 minutes to read the question first, and maybe you can try to attempt to find the answer, and then we discuss. Okay, give you around 4 minutes. So so we look at this example, linear displacement potentiometer circuit diagram shown in this figure. So it has a linear DC input of 5 volts, and the output voltage is 2.5 volts. So the total resistance element length is 100 mm. So when the sliding contact is at the center, the distance A between A and B to C is 50 mm. Okay, so the linear displacement of an object causes the sliding contact to move such that the output voltage change to 2.65 volt. Okay, determine the displacement of the object and the direction in which it moves. Okay, so it has given the, okay, so basically has give A, B, C, 5 volt. Okay, and then the total equivalent displacement is 100 mm. So when it's at half, A, B, and B, C, the position of the slider contact, the output is 2.5 volt. And the question is, when the V out is 2.65 volt, so what is the displacement? And is it moving up or moving down? Okay, so the need to relation between volt, and we find the relation between the uh, volt and millimeter. So relation between volts and mm is the maximum when it's the at maximum. So mm, or we can relate, okay, when BC at BC the displacement is 50 mm and the V out is 2.5. Okay, therefore the relation between the volt and meter is 2.5 divided by F50, so we get 0.05 volt per millimeter. Okay, so that basically the sensitivity lah. Okay, the sensitivity. So we get the sensitivity is 0.05 volt per millimeter. So what is when, okay, the change, okay, of 2.5 to 4.6, okay, and what is, oh sorry, what is the change when the output is changed from 2.65 to sorry, I changed from 2.5 to 2.65. So therefore the delta V out is 2.65 minus 2.5. This is basically a change of 0.15 volt. Okay. Therefore, okay, we can find the delta X from the sensitivity, and we find that the displacement is 3 mm. Okay, and so if we have to see whether it's moving up or moving down. So since this become more positive or increase, so it's basically moving up, or the displacement uh, is moving or towards A point. Okay, so that's how we solve this problem. Okay, now let's look into another problem. Okay, I give you another 3 or 4 minutes. Okay, so now the this is a voltage the potential divider circuit with the input of 12 volt, and the sliding contact is set such that the resistance across the output voltage is 8 kilo ohm, while the remainder of the resistance element gives a resistance of 2 kilo ohm. Determine the output voltage and then the scaling factor of the potentiometer at this setting. Right. So what is given is the input. Okay, the input is 12 volt. Okay, and the VR1 is 2K and VR out is 88K. So you need to find what is the V out, and then the scaling factor. Scaling factor basically the basically the sensitivity. Oh no, scaling factor is not the sensitivity, but the scaling factor is basically the output voltage divided by the input voltage. Okay, means that the output voltage at the given point, the divide by the input voltage. I mean the scaling factor at this setting. See, the scaling factor of the at this setting means that at this output correspond to the output of V out. Okay, so V out basically this is a voltage divider circuit. Okay, whereas V out is equivalent to V in multiply with R out over R in plus R out. Therefore 12 multiply with 8 over 2 plus 8. Okay, and you get 9.6 volt. So there are two ways to find the scaling factor. The scaling factor can be calculated in this setting. First, okay, from the V out over V in, or R out over R in plus R out. Okay, So V out over V in, or R out over R in plus R out. Because that's we can find the scaling factor. Therefore, in this setting, the output is 9.6, and then the input is basically 12, so we get 0.8. Therefore, the scaling factor is 0.8 or 80%. Okay. Okay, next we look into displacement transducer based on capacitive transducer. We know that the capacitive transducer is based on two conductive plates. They're separated by insulator. So insulator means that non-conductive material, or is based on insulation, whereas the capacitance of the transducer can be calculated by knowing the surface area of the between the plates, okay, and distance between the plates, and the type of the, or the dielectric constant of the insulator between the plate. Okay, and the formula is given by C equivalent to K multiplied with A epsilon naught over D, which is the capacitance, is proportional to the dielectric properties, also proportional to the area, and inversely proportional to the distance between the plate. So the sensing shaft in the capacitive transducer change the position of the dielectric between the capacitor plate in the transduction element. Okay, that's one method where the sensing shaft is attached to the insulator in between the plates. Okay, so when the insulator move due to the displacement of the object, okay, that link to the sensing shaft, so it will basically change the total value between the capacitive transducer. Or it can be due to the second condition, the distance, and also another case or another example is due to the total area, okay, change of total area between the plates. So it depends on the where the sensing shaft is attached. Okay, for example, in the second case, the sensing shaft is attached to the one of the plate, and then the plate is moving vertically. And the third case, the sensing shaft is attached to the top plate, and then it move horizontal direction. So this is one of the application where the capacitive pressure transducer is used to measure the fluid pressure inside the vessel. So in this example, it used to measure the fluid example where the the transducer consists of two flexible conductive plates and dielectric. In this case, the dielectric is the fluid. Okay, the fluid that move or contain in the vessel. So the one of the part of the plate, conductive plate, is connected to the positive, and another part is to the negative plate, right? So how it can be used to measure or relate with the pressure? Okay. So basically, when the pressure increase, so it will cause the plates to expand. Okay, when the increase expand, then change the distance between the plates. And okay, so we know that capacitance is in this case the change of distance d. So we know that the capacitance is change is inversely proportional to the distance. So when we can expect that when pressure increase, okay, due to the distance change, so the capacitance will decrease. But most importantly, that the change is proportional. Okay. So what we can basically do to basically convert this output into voltage. So a few options is use the voltage to capacitance to voltage. Hang on. So here we have a capacitance change due to the voltage. So the capacitance due to the pressure. And this application also it detect the human presence due to the basically due to the human that or subject that move sit on the car seat. Okay. So in this application, there is a sensing probe, which is one of the capacitor plate, okay, placed under the seat, and then the other plate is a fixed position under the seat. So another part of the seat, and then when the driver sit on the seat, basically it will change the distance or change the capacitance. In this case, is the capacitance of CP. Okay, so in this application, so it uses an oscillator, okay, to drive the RC circuit, okay, whereas the CP is connected to RC circuit. Okay, you can see the main oscillation supply pulse. So in a RC circuit, there will be a transient response before it reaches the final. Okay, when the capacitance fully charged, so the output will be equal to the amplitude, and when oscillation is moving or discharge or change from positive to 0, so the capacitor will be discharged. So that's basically the output, okay, oscillator. Okay, so this output EX, okay, RC, and then is given to the negative of the operation of empire, and then another capacitor is used as the reference, and then use the similar input, okay, and given to a reference capacitor CX, and the output of the CX, sorry, the output of the in this EP, and this output is EX. So when the basically CX is a very variable capacitor. So the calibration is done by basically capacitor is calibration is done by when there is no occupant on the seat. So CX value is changed so that the EX and EP is in phase, okay, so that the output of VC is equivalent to 0, okay, when there is no occupant. And when there is occupant, so CP will change, and we will produce an output pulse, small output pulse of VC, and will compare to VREF. So we'll trigger the detection of the occupant. So this is one application where it's used to detect or to convert the capacitance change into voltage, okay, voltage output. So there are other way you can use, like to change the voltage into the capacitor change into voltage, like using voltage capacitor to voltage converter using RC feedback. And also we have a similar device. It is basically a simplified LVDT device. So in this case, there is only one set of secondary windings, whereas the output is proportional to the change of inductance. Okay, so similar to LVDT, it is used to detect or to monitor the condition or the gearbox in the for example in press feed process. And we have optical displacement transducer. So it is based on the measurement of intensity of the reflected light from the target. So in this application, we use a light as a source, where the light is a semiconductor device that emit irradiation, light irradiation at certain wavelength. So basically, the intensity of light, okay, that travel from the transmitter to the receiver, okay, depend intensity that travel depends on the total path length. Okay, so basically the output or the output is exponentially decrease with the distance. So that's a Beer-Lambert law. Beer-Lambert law. Basically, when the distance is further, so the output signal or the irradiance will reduce or decrease exponentially. Okay, so it can be used as a displacement transducer, whereas for example, in the case here where the transmitter and receiver is placed towards a reflector, so as the reflector move away, so the total path will increase. So the output is inversely exponential relation have a exponential decrease exponentially with the path of the optical signal. And then there's another device where this used based on optical. It's called as laser interferometer. It is based on laser technology, where it utilizes wavelengths as a measuring unit to achieve standard of accuracy, precision, and repeatability. Meaning that it is a high or very high accurate device, so especially in measuring displacement. Okay, so this is the principle of interferometer. Basically, it consists of a light source, beam splitter, two mirrors, okay, and a lens, and also a detector. So what happened? So basically, the light will come to separate by the beam splitter, and then will basically reflected back the mirror 1 and mirror 2, and the reflected signal will be focused, okay, on the detector. And the detector basically the when the distance is the same, okay, so it used as its reference. But when the one of the mirror is displaced, let's say to the left, so the detector will sense a different pattern, okay, different pattern or respond. So this is basically the light, which, okay, due to the different pattern or light sensed by the detector, okay, it is used or is sensed by the detector. So it will depend on the what is called as the uh, increase or decrease of interference. Okay, so the movement of the second mirror, okay, it will cause the interference to increase or decrease. So basically, when the first and second mirror has a same distance, so the interference is low. So when as the second mirror move further away from the beam splitter, so the interference will be increasing. Okay. So this is used for a greater or accurate detection of movement, uh, for to move to check the movement of a surface. Okay, like hard disk. Okay, so hard disk, especially hard drive based on the rotation. So we will it can be used to detect the slight displacement, or if the increase of displacement because of the vibration, it can be detected by the by the interference from the detector. So it is a very high resolution, around 0.08 nanometer. And there's another device, strain gauge, where this is another device which is used to detect displacement. Basically, this device, the electrical resistance very proportional to the amount of strain. Okay, strain is basically there's a fundamental parameter. Strain is basic. It is sensitive. This device is basically sensitive to strain, and it is basically uh, expressed as the gauge factor. So that's the strain. So basically, the change when this device is subjected to strain. Strain means coming from object or force. So it will change the resistance. So the resistance over the total resistance of the sensor, or the nominal value of the resistance, divide by the change of length over the total length. So that's the strain. And then the gauge factor for metallic strain is around 2. And this device can be uh, can be converted into output voltage by using a Wheatstone bridge as shown in this figure. Okay, where the output V out, okay, is in the function of the gauge factor. So gauge factor is basically the strain or the chain of deformation of the construction when it is subjected to force, okay, or object, heavy object especially. Okay, so some of the application is can use to detect the angle or helicopter blade angle sensor placed to check the condition. Okay, this is not, that's a strain sensor. So we take about 5-minute break.